And we are now recording.
Okay, Gil, there's 34 people, so let me introduce you so long.
Yes.
Since we're recording, and then we can yeah, I think it's fine. It's 4 past already, so I think it's fine if we begin. So welcome everybody. This is a seminar webinar by Professor Gil, organized by Working Group 4.2. So we are the group on artificial intelligence and uncertainty modeling in spatial analysis. So very aptly, we have Professor Gil coming to speak to us today. He is a professor at Clark University in the Graduate School of Geography. And he creates quantitative methods to contribute to GIS, remote sensing and statistics. He's effectively an applied statistician, an environmental scientist with experience in GIS, ecological modeling, and land change science. He has derived various mathematical proofs concerning measurements that are essential in various fields, and several of these methods have been incorporated into the GIS and image processing software TerSet, which has over 100,000 users worldwide. His solo authored book is entitled Metrics That Make a Difference: How to Analyze Change and Error, and his collection of videos helps to disseminate his work. So if you joined a little bit earlier, you would have already enjoyed a discussion about Kappa. And if you missed it, we already had a sort of discussion in the chat about Death to Kappa, the paper. So you were in the right place if that is a paper that you've read. So I'm going to hand over to Professor Gil. I'm told I'm calling him Gil, not Robert. So thank you, Prof. Over to you.
Hello, everybody. From Massachusetts in the United States. The title of the talk is Kappa the Undead. Let me explain that. Some of you might know that my most highly cited paper is entitled Death to Kappa, which Marco Millones and I published in 2011. And since that time, we've done a literature search on the papers that have cited that paper, and I'll present some of those results today. And those results show that it's been remarkably difficult to kill Kappa, and Kappa still is haunting the profession like a zombie, thus the title Kappa the Undead. I've just recently written a sequel to the Death to Kappa paper that I just submitted to the International Journal of GIS under the same name. So hopefully you'll be having a publication on this pretty soon. So Kappa the Undead and the inconsistent adoption of insightful error metrics. Many of the materials that I'll refer to are on my website here. I'd like to thank NASA and the National Science Foundation and MAP Biomass and the Fulbright Foundation for generous funding. Well, let me get right to the main points here. I've got 5 recommendations for you. You need to design scientific questions and methods so the results are important regardless of the conclusions. You have some self-interest in this because presumably if you're a student, you would like to graduate, and presumably if you're a researcher, you'd like to publish an article. So if you design your research question and method so the results, if they turn out one way, they're important, and if they turn out the other way, they're important. Then either way, you get to graduate and you get to publish your paper. If you've designed your research question such that you already know what you're going to conclude, then you're not doing science. Recommendation number 2, report components of difference rather than a measure of agreement for error assessment. And I'll describe some of those components of difference in this presentation. Measure change during time intervals rather than presence at time points for a time series, which I will illustrate that concept. Report the reliability of the reference data and search for suspicious data using methods such as trajectory analysis, which I'll explain. And it's almost embarrassing, I need to put point number 5. Read the publications that you cite. I've got a question for you. Describing results as acceptable or not is inherently unscientific. Do you agree, disagree, or have some other type of response to this multiple choice question? And Lakshmi will activate our poll so we can see some results from our audience members. That's your cue, Lakshmi. There we go. You can answer exactly one of those, single choice. And Lakshmi, are the results coming in? Lakshmi, are you there?
Yes, the results are coming in. This is triple.
Okay, we'll give it another 10 seconds. Quick question here. Okay, let's close the poll and see the results.
Can you see it, Gil?
Okay, we got 73% agreeing, 19% disagreeing, and 8% other. Well, when I took 8th grade science, a fundamental concept was that if you're conducting a scientific question, you go and collect data and you report the results. And it would be absurd, I think, for someone to say, oh, those results are unacceptable. So I certainly agree with this statement. But what I find shocking, I regularly see in the literature that people say, well, we did this classification and these results are acceptable. It's like, and then they use a metric such as Kappa. Sometimes they'll use percent correct. And then they give an arbitrary threshold of that metric of 0.8, 0.5. I've seen all sorts of levels of a metric, and they anoint their results as acceptable. But I think there's a fundamental problem with that. Even if you're thinking that scientific results can be acceptable or not, you're not doing science. I got another question for you. Which of these comparison maps agrees more with the reference map? So I'm using the word reference on the left to mean data that you think is the best available data. And then you have two other maps. I'm a raster GIS kind of guy. So I have 10 pixels of reference data or the presence or absence of a category, a blue category. It's denoted by the number 1, and what's not blue is denoted by 0. And then I have, let's say I have 2 classifiers. And I make using one classifier, I make a map called comparison 1. Using a different classifier, I make a map called comparison 2. I've got a question for you. Which of these 2 comparison maps agrees more with the reference map? Again, multiple choice questions. Comparison 1, comparison 2, or other? That's your cue, Lakshmi.
Yes, so I'm going to start the poll 2.
Yes. Okay.
Sorry,
Yeah.
it's just coming up. I have to
it came up for me and then it disappeared.
Okay, it's coming again. Sorry for technical glitch. It's here. Poll 2. Can you see it now?
I can see it now.
Feel free to respond.
Okay, I think that's enough time. Let's see what the results are.
Okay, I'm sharing the result.
Okay, we've got 7% for comparison 1. There's always some. 69% for comparison 2 and 24% for other. Well, that's sort of, I've conducted this poll elsewhere, and those results are somewhat representative. Here's how I'd answer that question. I would select other. because this phrase agrees more, in my opinion, is just insufficiently precise. I don't even like the question because it focuses on agreement. But we're likely to learn more from the difference than from the agreement. So I've had people come to me and ask me, Gil, I need a number, and I want this number to show that my results are good or acceptable. So therefore, the number has to be between 0.85 and 0.95. And because many authors want to use an index ranging from 0 to 1, where 1 means perfect agreement and 0 means something else. And if they claim perfect agreement, no one's going to believe them. And if they have some number less than 0.85, then they're afraid that people will say that their results are no good and they're not going to be able to get their paper published. So there's lots of indices that are designed to address this question about which of these two comparison maps agrees more with the reference map. Let's go to Wikipedia. Wikipedia has 20 indices for this situation of two classes. A very popular index is percent correct. So if you look at percent correct, well, comparison 2 has 8 of the 10 pixels in agreement. Comparison 1 has only 2 of the pixels in agreement. So by the criterion of percent correct, then comparison 2 is a better agreement. But if you like percent correct, well, consider this. Would you consider a map that's completely yellow to be even a better agreement with the reference than comparison 2? Well, maybe you would, but percent correct even has its own problems. So you can maximize percent correct by overestimating the majority category. So in this case, the majority category is yellow. If you just make your map completely yellow, then you're going to have an even higher percent correct with the reference map. But I'm not sure whether people would necessarily say that that would be a better agreement. So, but people still use percent correct, and they don't focus on the reasons for the disagreement, but they tend to use percent correct and another metric called Kappa. Let's see what Kappa has to say. Kappa is an index that ranges between 1 and -1, where 0 means that the agreement is equal to a random spatial allocation. So according to Kappa, Kappa is positive for comparison 1, negative for comparison 2. So maybe some of those of you who said that comparison 1 agrees more are Kappa lovers, because Kappa says that comparison 1 is in better agreement with the reference than comparison 2. I've seen many people use Kappa, and I regularly go to conferences, go to poster sessions, and I ask people why they use the metric that they did. And if the metric is Kappa, I get some typical answers. And those answers are, this is what people do in my profession, or this is what my supervisor told me to do. And those two reasons are social reasons. Those are not scientific reasons. If you select a metric based on its popularity, then you are likely to do absurd things, meaning you're going to probably repeat the same mistakes that have infected the profession. You need to, when I ask people why they've used the metric they have never told me, because this metric answers our research question. So what you must do is to align your metric with your research question. If you try to do this, you're likely to realize that you have a vague research question, in which case you have learned something. You need to revise your research question. People tend to use kappa or percent correct and then say, well, a kappa greater than some value, 0.7, 0.5, 0.8. I've seen all sorts of claims in the literature, means that the results are acceptable. Any universal rule for selection of a particular metric and the value of that metric for acceptability is absurd, because any universal rule is not connected to any particular research question. We have in our profession become infected by this mentality that universal rules exist for acceptability. And one of the biggest problems is with percent correct. And Anderson's recommendation that percent correct should be greater than 85% is absurd and has caused horrendous damage to the profession. Even using the word should in science is inherently unscientific. Results are what they are. The results aren't obligated to be any particular way. I think people need to focus on the reasons for the disagreement. If you look at the reasons for the disagreement, the reason why comparison 1 has 8 of its pixels in disagreement is because comparison 1 has the wrong amount of blue. Comparison 1 has 9 pixels of blue, and the reference has 1 pixel of blue. So that all of the disagreement, the 0.8 of the disagreement, is the fact that it got the wrong quantity. Whereas for comparison 2, look, it has the perfect quantity. It has 1 pixel of blue, and the reference has 1 pixel of blue. So the quantity is perfect. There's no disagreement of quantity. It's just the spatial allocation of the disagreement is 2 pixels. If you exchange the position of these 2 pixels, then you eliminate the disagreement. And that type of disagreement is called allocation disagreement. So all of the disagreement for comparison 2 is allocation disagreement. I just find it much more helpful to think in terms of these 2 components of disagreement rather than presenting a metric of agreement. And this is one of the recommendations that was in the Death to Kappa paper in 2011. In fact, there were 2 recommendations. Don't use kappa, instead use these components of disagreement. So if you think about it, I said that the question of which of these 2 maps agrees more is insufficiently precise, because your criterion needs to specify the purpose of why you're mapping. If your purpose is to estimate the quantity, then comparison 2 is actually perfect, because you have the perfect quantity, 1 pixel of blue, and all the rest are yellow. So in fact, even percent correct can be misleading for your particular purpose, because if you had another map that was completely yellow, it would have a higher percent correct that would get the quantity wrong by 1 pixel. Okay, so my doctoral student, Marco Millones, and I, in 2011, published this Death to Kappa paper. It had 2 messages. Don't use kappa, and instead use quantity and allocation disagreement. The Death to Kappa paper now has more than 2,000 citations. Where did you think? Oh, I might be happy about that. Here is the abstract of the Death to Kappa paper, part of the abstract. This article concludes that these kappa indices, there's actually several kappa indices, are useless, misleading, and/or flawed for the practical applications in remote sensing that we have seen. After more than a decade of working with these indices, we recommend that the profession abandon the use of kappa indices for purposes of accuracy assessment and map comparison, and instead summarize the cross-tabulation matrix with 2 much simpler summary parameters: quantity disagreement and allocation disagreement. And so I thought that was pretty straightforward. And then I started seeing how people were citing the Death to Kappa paper. Here's one example from Gao. The kappa coefficient has proved to be an excellent statistical parameter for measuring consistency. Like, what? Not only did these authors miss the point of the paper, they emphatically said just the opposite of the paper that they cited. And they're not the only ones. Here are more examples. I even got another one this morning from Kappa. But Kappa in 2020 writes, the Kappa statistic and confusion matrix were calculated for accuracy assessment, which is thought of one of the best quantitative measures of image classification. It's people, and then other people copy Kappa. One of the best quantitative measurements known as Kappa. Confusion matrix and statistics are among the best. These people are citing a paper entitled "It's a Kappa paper." They have apparently not even read the title of the paper that they are citing. So I wondered whether or not these citations were representative. So I worked with one of my students, Francis, and we sampled 200 articles that cited the Death to Kappa paper. We tagged each of the articles concerning whether or not it adopted the first recommendation to abandon Kappa and whether or not it adopted the second recommendation to use difference components. We recorded also the article's year, country of the first author, number of citations, and publisher. So here, of those 200 articles that we sampled, here are the journals from which they came. The most common one was remote sensing. Many articles also International Journal of Applied Earth Observation and Geoinformation. And we've got some real top journals here. So let's see, look at the results. The 200 papers, a quarter of the citations fall into each of the four combinations, whether the authors followed each of the two recommendations in the Death to Kappa paper. A quarter of the papers followed both of the recommendations. A quarter of the papers followed only the first recommendation, meaning they did not use Kappa. They didn't use difference components. A quarter followed only the second recommendation, meaning that they used Kappa and reported the difference components, and a quarter of them followed neither of the recommendations in a paper that they cited. Furthermore, what was fascinating is the results were remarkably consistent across the year and the country and the number of citations and the publisher. Because, some people said, oh, the investigators from this country don't know what they're doing, but we didn't find any evidence of that. Some people have told me, this publisher is not reputable, their papers are bogus. We found that Kappa is an equal opportunity zombie. It haunts people across the globe and across publishers. Even more concerning, half of the papers that reported quantity and allocation difference failed to interpret the difference in a way that relates to any research question. They merely reported the numbers and then anointed their results as good. Many papers reported the metrics, then concluded that the results are acceptable by claiming that Pontius said a specific value of a particular metric is acceptable. None of my literature has ever said any particular value of a particular metric is acceptable. I've never used that word. And furthermore, I've never seen that word applied in an intelligent manner, where the word acceptable is defined in relationship to a particular research question. So there's a cascade of social forces that generate this bad science. It's coming from a variety of actors. Even employers' criteria for hiring and promotion include number of publications. So authors find themselves under a lot of pressure to publish a lot of papers fast. And authors think that high accuracy and many citations of famous authors are necessary for a paper to be accepted. And they're not completely wrong, because reviewers give superficial reviews because of negligible rewards for reviewing. Furthermore, even the publishers have problems. Journals get their status by having a high impact factor. So journals facilitate citations of their journals regardless of whether the authors obtain the article. If you go to the journal's website of where the Death to Kappa paper is, you can click a button that asks you to pay money to get the PDF, but you can click another button that you can cite the paper for free. So journals facilitate you citing a paper that you haven't even read. I have another example here that Kappa is frequently used for validation of land change models. So here I have an example of a two-map validation of a land change prediction. It shows that the proportion correct is 0.7 and Kappa is 0.67. So we have, I do a lot of land change modeling where people are predicting the change from a time 1 to time 2. So they have a time 2 prediction map and a time 2 reference map. And here, each of the 10 pixels, each of the numbers represents a particular category. So if you compare these two maps, then in the first pixel here, well, that's wrong. Second pixel is correct. The third pixel is that's wrong. And the fourth pixel, that's wrong. And all of the other pixels are correct. So in percent correct, it's 70%. Kappa is 0.67. I saw a paper this morning that just claimed that Kappa greater than 0.5 for predictive accuracy is acceptable. And they cited one of my papers inappropriately. So if you think about this, well, there's a fundamental flaw in this, in that the land change model was predicting the change from a time 1. So say this is the time 1 map. And so this is the time 1 map, and these are the categories. Let's see where the model predicted change. The model predicted change only in these pixels here. So in first pixel, it was originally 1, and the model predicted that it would remain 1, but in the reference, changed to a 3. So there was a change, and the model missed it. So it'd be helpful to just call this a miss. M stands for miss. Let's take a look at the next pixel. Started out as a 1, the prediction said it was a 2, and the reference said it was a 2. So that's a correctly predicted change. That's a hit. Let's take a look at the third pixel. Started out as category 1. The prediction is that it changed to category 3, but in actuality, it changed to category 4. So the model predicted correctly that it changed, but the model got the wrong gaining category. So that's a wrong hit, W. The fourth pixel, it starts out as a 1. The prediction is that it changes to a 4, but in actuality, it remained a 1. So the model made a false alarm, falsely alarmed that there was going to be a change. So that's a yellow. All the rest of these are correct rejections, because if the pixel did not predict, for this pixel, there was no predicted change. No predicted change happened in actuality. So all of these gray ones, they are correct because there's no change that occurred. I think it's much more helpful just to report how many misses, hits, wrong hits, and false alarms there are in the data. And so what we see here is we have more error than correctly predicted change. The errors are the misses, wrong hits, and false alarms. And we only have one pixel correctly predicted change. Now, I made that illustration because I was originally motivated at a conference that I attended where people were telling me continually that their model performed well, but they had no definition of that. And so I organized this international collaboration where we invited land change modelers to submit 3 maps: a reference map of time 1, a reference map of time 2, and a prediction map of time 2, and a criterion to evaluate the maps. And we immediately got some interesting results. Many of the scientists promised to send us the maps. Few of those scientists actually sent the maps. Of the scientists who sent the maps, few sent any criterion to evaluate the maps. And those who sent the criterion usually sent for percent correct between the reference and prediction at time 2, making the blunder that I just illustrated. So we got these maps, and the people trusted me to do this analysis. And so here's an example of my model, the GeoMod land change model in Worcester, Massachusetts, where Clark University is, with that exact same legend with those colors. This red patch, those are the hits. That's a correctly predicted change. Yellow is an error. Yellows are false alarms. Blues are misses. And grays are correct rejections. So what we have, there's more error than correctly predicted change. And so I always show this first to say, okay, well, here's the results that I got from my model. I got more error than correctly predicted change. Now let's see what some other models have. We had 13 applications that show 12 countries. We have 13 applications show that 12 of the applications had more error than hits at the resolution of the data. And here from where the applications come, and here are the results, those 13 applications. On the horizontal axis is the percent of the landscape, and on the vertical axis gives each of the 13 cases. And we have stacked bar here, which is the same colors that I presented before. The blues are the misses, the reds are the hits, and the yellows are the false alarms. So the observed change is the union of the blue and the red, and the predicted change is the union of the red and the yellow. And so what we had is there was only one case that had more hits than error. And that was this one case from Madagascar. And so we, in 12 of the 13 cases, had more hits, more error than hits. So I presented this results at International Conference of the Global Land Program, and I was introduced, my person who introduced me said, now here's Gil, and he's going to tell us how bad our models are. And I'm like, oh, God, that's not the kind of introduction I was looking forward to. But I presented these results around the world, and we've given workshops on this with the people who participated in this. And I tend to get two types of responses from those presentations. One is from the non-modelers. They come up to me and say, God, your colleagues must hate you. But from the modelers, I get quite a different response. The modelers say, thank you for exposing this, because now I can publish any results, which that really taught me something. It taught me how much pressure authors felt to claim that their results were good and that they had to have their results come out a certain way in order to get published, and that they were under a lot of pressure to publish. But through this exercise, we freed people that you can do good science. In fact, in order to do good science, you must publish the results that you get, and it's not necessary, and it's actually not legitimate to call your results good or acceptable or unacceptable. Just present the results as they are. So there's another problem in the profession when using some of these metrics that when people have a time series of maps. And typically what people do is use percent correct on maps at time points, which is a distraction when analyzing a time series. When we have a time series, we want to know primarily about the change and secondarily about the stability. Percent correct at time points gives information about neither change nor stability. So the following slides will show how if a class is 90% correct at each of 2 time points, then change during the time interval can range from perfectly correct to perfectly wrong. So here what I have at the top is 2 confusion matrices for a start time and an end time, where in each confusion matrix, we have the presence or absence. And the rows are in the map and the columns are the reference data. H stands for hit, F for false alarm, M for miss, and C for correct rejection. So the errors are the misses and the false alarms. I have uppercase letters for the start time and lowercase letters for the end time. So some people say, oh, my maps at the various time points are better than 85% correct. So now I'm going to overlay the maps and pretend that the temporal difference is real change on the ground, which is just an absolute fundamental blunder. So let's see how these errors at the individual time points would translate to a confusion matrix of the time interval. If you have a time interval, you can either have stable presence, loss, gain, or stable absence of the category. And depending upon how the uppercase letters at the start time are paired with the lowercase letters at the end time, and the results at the individual time points will lead to this confusion matrix for the time intervals. So let me give an example. Let's say that error exists at both time points. And let's say you have 10% error at the start time and 10% error at the end time. So you have 5% misses, 5% false alarms, and 5% misses, 5% false alarms at the end time. If all of these misses happen at the same place as these misses, then all those errors end up here. And you're confusing stable absence with stable presence. If all of these false alarms happen at the same place as these false alarms, and that results in this in the confusion matrix. Again, you're confusing stable presence with stable absence, in which case you get all the change correct. However, if you have, let's say, 10% of your error is these false alarms, and they happen at the same place as the errors here that are misses, then you have the false alarms paired with the misses, and so that error is here. And so your map says loss, where all the reference data shows gain, in which still your maps at the individual time points are 90% correct. All of the change is perfectly wrong. Or the change can be wrong in the other way. All of these misses are paired with those false alarms. Then all of your map says, where the map says there's gain, the reference data shows that there's loss. And so information at the individual time points is just not helpful to understand the accuracy of the difference during the time interval. Now, another pet peeve of mine is when people make claims about their accuracy, but they don't give us any information about the reliability of the reference data. So Dr. Foodie has been beating this drum for years. I think it's time that we listen to him. Your reference data might be unreliable to the degree that correct and error actually make no sense. And why? Because it's remarkably difficult to collect good reference data. I've been working with my doctoral student, Ian Zhang, she's trying to make a classification of a time series of water versus not water. And we've used images to collect reference data. And so these are raster data, half-meter resolution pixels. And we have these 3 time points. The black dot is at the same place at all 3 time points. And, well, water tends to be dark, and shadows are also dark in these images. So if you do a visual assessment, then for each of these dots, is it water versus not water? We have to make a visual assessment. Well, one thing that we've learned is that the images are inconsistently geo-registered. So here it looks like there might be a pond that's migrating. The images are misregistered by, maybe a couple meters, which is more than the spatial resolution of those pixels. So we had various interpreters look at this and give different assessments. Even the interpreters knew that they were uncertain, which means that the reference data are unreliable, which means you shouldn't even be reporting anything about percent correct or Kappa. So Ian recently has been now beating this drum that people shouldn't even be talking about accuracy if their data are unreliable. She's not claiming that her maps are accurate. Can she get published for that? Not only can she get published, she can win awards. So the American Association of Geographers just awarded Ian first place for her work in how to show the unreliability of the reference data. I think we need to follow Ian's lead in this. The time series data are easier to generate than to assess for accuracy. Reference data are really complicated and costly to collect. But now we have such long times, we have satellite imagery that allows us to make these long time series, but the reference data are too costly to collect. So what do? Well, we can still examine the data to see whether they make sense as long as we use an insightful method to examine the data's patterns. One such method is called trajectory analysis. So let me show you what trajectory analysis is by this application in Western Bahia, Brazil, which is a hot spot for soybean cultivation. So MapBiomas makes data available through a time series. And one thing, so we have the data, and we can just look at the data to see if they make any sense. But what we immediately see is that the data are so enormous. We have maps that show the presence or absence of soybean at 33 individual years. So the extent has more than 200 million pixels, and each pixel has more than 8 billion possible combinations of the presence or absence of soybean. Well, how do we assess the quality of those data? They're so enormous. The reference data are too costly to collect. And so what we need to do is to design a method to see whether the data just make intuitive sense. And one thing that many people do is to get the data and to show this plot. And so this shows the quantity of soybean at these various time points, but this fails to show the spatial allocation of the soybean or whether or not the soybeans are alternating. Alternation is when the same place alternates between presence and absence through the time series. And this plot doesn't show us anything about the reliability of the data. So my doctoral student, actually he's now Dr. Thomas Spilento, he just graduated this last May. He created this method called trajectory analysis. So it produces one map that shows 8 trajectories for these 32 time intervals. So here's the map. And the trajectories, well, the most common one here is gray, stable absence. The next most common one is the dark blue, gain without alternation. That means through the time series, there was one point that there was gain, and then it stayed presence. And there's another color here, light blue is gain with alternation. It means it started as absence, it gained and then lost, and then gained and then lost, and then finally gained and ended as presence. The bright yellow is all alternation, gain first, meaning it started as absence, then it gained, lost, gained, lost, gained, lost, and then the last change was a lost. It ended in absence. So the map allows you to see where the change is occurring. In this, the plot on the right, the bars can show when. The bars that extend above the horizontal axis are gains, and bars that extend below the horizontal axis are losses. So what we see are some of these years where, wow, we have a big gain followed by a big shrink in the loss. And so when we look at these patterns here, especially some of these enormous changes at the end, we can look for suspicious patterns. And then that will allow us to focus to look more closely at data quality. And we can do this at the annual resolution. And so this is the annual resolution, and we can also coarsen the temporal resolution to look at 2-year intervals. And as you coarsen the temporal resolution, then sometimes you might be eliminating data that you don't even believe. Another output of this is it shows at each of these temporal resolutions, shows how much change you have, how much change is attributable to each of these components. The quantity component here shows that overall there was a gain in soybeans. The alternation is what I was describing earlier. That's places where pixels alternate between presence and absence. So what we see is that the alternation shrinks as you go to these coarser temporal resolutions, which, I think that probably means we actually believe the data at these coarser temporal resolutions. So there's plenty more to say, but we're going to have time for questions real soon. Get your questions ready. One of the things I recommend you do is go to my website, get this book, and start with the chapter entitled Commandments to Avoid Deadly Sins. It's my first book, and I hope you find it helpful. And so again, to summarize, here are my recommendations for error assessment. Design the scientific questions and methods so the results are important regardless of the conclusions. Report components of reference rather than a measure of agreement or error assessment. Measure change during time intervals rather than presence at time points for a time series. Report the reliability of the reference data and search for suspicious data using methods such as trajectory analysis. And at least, at the minimum, read the publications that you cite. Thank you.
Thanks, Prof. That was really, 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 really interesting. Our chair of our group is Mahmoud. I don't know, Mahmoud, if you want to say something.
Actually, I would like to thank Professor Pontius for his very valuable presentation. And we had before this several presentations from Professor Pontius in our conference in Tehran and also in other webinars. Now, I would like to ask two questions from Professor Pontius. When we compare this agreement and disagreement maps with different indices to evaluate Kappa with other indices, now we are facing with the massive use of artificial intelligence for data integrations and data fusions in remote sensing. And now a lot of research has come, for example, to integrate different methods and different parameters. What do you think that how we can find out the perfect measure for these data fusions in, for example, change detections, land use land covers, and also what we can comment with the massive methods in data integrations, even in ChatGPT's different publications. Now we see in the scientific community that we cannot differentiate easily between what is perfect, what is not perfect. What do you think about these issues, and what is your recommendation?
Yeah, well, my number one recommendation was that number one, as I concluded, you need to select a metric that matches your research question. And I think researchers are going to find that remarkably difficult. I've been involved in a land change modeling project for 2 years now with some phenomenal experienced modelers. And it's taken us 2 years to debate what's the appropriate metric. And we're still not completely satisfied. And my concern with what I see in a lot of artificial intelligence presentations that I go to, people, they have their metrics, and when I ask them why they're using that particular metric, they give me the same answers I've gotten elsewhere, that this is the metric that we use in this profession. And they don't know exactly why. And even when I ask them to define the metric, and they can't tell me. And so I think this is a problem throughout science, that people use a metric out of habit. They use it because other people do. And it's become a real problem. And when you combine that with a mentality that people have to claim, they think that they have to claim that the results are good somehow, then it's just, there's no learning that happens. And so I think people just need to slow down and think really carefully what their research question is, and realize that that exercise is difficult. They have to also realize that it's remarkably difficult to get reliable reference data. And so my concern with so many artificial intelligence procedures is they increase the number of petabytes people analyze, but they're not increasing the amount of intelligence people are using to analyze that. Okay, so I see some questions in the chat.
Sure, I'm going to read them out loud, and then so that everyone can
great.
hear them, and then you can respond. The first one is from Conrad Schindler. Regarding your meta study, so that was at the beginning of your presentation when you took that sample of 200 papers. Do you think it is problematic that people don't use Kappa and don't follow your second recommendation? Perhaps they agree with the diagnosis that Kappa is flawed, but came to the conclusion that for their specific question, other metrics are better alternative than quantity and allocation disagreement.
I would love to see such a paper that makes such a claim, because it means that the person actually thought about the research question and then selected a metric for that particular research question. Typically what I see is people, if they don't use Kappa, then they'll just select some other metric that's popular with no particular justification. But I'd love to see papers that say, we've thought about the research question and this particular metric addresses our research question, and that's why we used it.
Agree. Richard asks, dear Prof. Pontius, thank you for this great talk. What are your thoughts about geometric errors when using an object-based approach? Not necessarily due to the inconsistently georeferenced images, but also due to the different shape of, for example, polygons between different years. Also, when the percentage of each land cover inside a polygon is not so different, for example, a class covering 70% of the polygon versus another one covering 30%, although one is clearly dominating, the remaining 30 is still very relevant.
Okay, so I recommend you read a review paper by the first author is Su Ye, and the last name is Y-E, and I'm a co-author, and Rahul Rakshit is a third author. We did a review of 200 papers that are concerning methods for accuracy assessment for object-based image analysis. And through those papers, I haven't found any really elegant, straightforward way to address error assessment when you're taking in consideration the polygons. The methods that I've seen devolve into just an overlay. You can just rasterize the maps or take a random sample of points. And then the method is just like other methods. So if you know of a method that's elegant and that compares the polygons, then I'd be interested in it. Some of the methods that I've seen, it says, well, you need a one-to-one matching between the polygons of your map and the polygons of the reference data. But typically, you don't even have the same number of polygons in the map with the polygons in the reference data, so it's impossible to have a one-to-one matching. So I think a lot of people are wrestling with that, and I haven't yet seen an elegant way to take into consideration the shapes of those polygons.
Jonathan says, thank you for your presentation. Do you have a particular strategy for developing the right metric once you have identified the right research question? Lovely.
Yes, that's good. Be prepared for it to be a circular feedback, meaning that you have a question, you think that you can answer the question with a particular metric, then you look at that metric and then you realize, that doesn't quite measure what we want. You might have to go back and revise the question or go back and revise the metric. But I think that will be a phenomenally helpful exercise because you'll learn a lot about what your particular goal is. And what I always do is search for the simplest possible way to address the research question. And because that makes things clear for both the researcher and the reader. So I think you can look to see what people have done, but that can be dangerous because you can get lured into just doing what other people have done. But I'll tell you this, it will be challenging, but it will be a learning experience. Thank you for your question, John.
Chucks has got his hand up. Go ahead.
Yeah, so can you hear me?
Yes.
Yes. Thank you, Professor Gill, for
Yes.
the wonderful presentation. So my question is, obviously, since your publication of Death to Kappa, and in the results you presented in that analysis of 200 papers, and what authors, those who are following the recommendation or not, obviously, new information like this, it takes a lot of time for it to permeate within the research community and scientific community. And, what suggestions do you have, or how do you feel that important knowledge like this, which is actually very, very important, and influences the quality of science, how do you feel it should be disseminated, or how do we make it gain a foothold more, within the scientific community?
Yeah, that's exactly why I'm doing this webinar, because I've tried other things with partial success. I mean, one thing I've learned is publishing journal articles is not a panacea. Publishing journal articles is necessary, but it's not sufficient. Yeah. So if you come to a conference where I am, take my workshop. Every time I go to a conference, I give a free workshop. I've got webinars that are now listed on my website. I was pleased at least the Death to Kappa paper, at least some people were paying attention to. I mean, I go to conferences and I say, why did you use Kappa? And they say, oh, Death to Kappa. And they've heard the phrase, but it doesn't translate to not using Kappa on their poster. But reading some of these where people make a publication and they emphatically claim just the opposite of the paper that they're citing means that some people, they're not even reading the titles of the papers that they're citing. And so with those authors, it's hopeless. I just think that you can't get through to them because they're not in this for science. They're in it to keep their job, to get their promotion, but they're never going to make any progress. They're never going to be leaders. So you need to pay attention to the literature and what some of the leaders are really saying. I mean, like I said, Foodie has been beating that drum for years that we shouldn't be trusting our reference data. But I almost never see any publication that says, here's the reliability of our reference data. Publications are constantly saying, oh, our data are good. Another great leader is Professor Steve Stamen, who is actually on my doctoral committee. He's a professor at State University of New York, College of Environmental Science and Forestry. And he recently led a publication where they claimed clearly in the abstract that the accuracy at the time points of a time series was, 85, 90%. But the users and producers' accuracy of the change during the time interval was less than 20%. So it is possible to get published with reporting low levels of accuracy. And in fact, I think even as readers and reviewers, if someone is making claims that are not justified, we just, as a reviewer, just reject the paper. If someone makes a claim that their results are good, using a metric for which they don't have a justification, just reject it. There's been some success that I have a friend, Jeju, who's associate editor of Remote Sensing of Environment, top journal in remote sensing. He says, as an editor, if he sees a submission that uses Kappa, it's an automatic rejection. So I guess it's time for people to get hardcore, to So people start thinking, if I use Kappa or if I make unjustified claims, I will get rejected. And if I cite literature just to have long lists of publications, that should be a sign for rejection. I'm proposing in this paper that Kappa the Undead paper, I'm proposing that if an author claims that the results are acceptable or good or unacceptable, that should be grounds for automatic rejection of the manuscript. Because acceptable or not acceptable or good has no place in a results section in a scientific paper.
Thank you.
Agree. Couldn't agree more. Chucks?
Yeah, thank you very much.
There's lots of thank yous in the chat for you, Prof. Anybody else want to ask a question? You're very welcome to also put your hand up and I'll unmute you if you want to ask a question live or with your voice. Okay, Prof, I don't see any more questions. Nope.
Okay, well, you know where to find me at my website. I presumably ISPRS will post a video of the webinar and spread the news.
One more.
So you said, Chucks has one more question.
Yes. Yeah. Something came up. So recently I was reading something else. You know, I was reading this concept of planetary boundaries, which was proposed sometime in 2009 by some scientists. You know, where Earth system boundaries, planetary boundaries. You know, basically where they're trying to look at some sort of thresholds in these different components or boundaries in the Earth. You know, and you want to reduce stressing a particular planetary boundary, you know, to avoid some hazardous or catastrophic effect in the environment. And then I noticed there was some criticism of that concept, you know. And when you look at some new ideas or some new things that are proposed in science, sometimes when you look at the criticism or the acceptability or the otherwise, sometimes you notice there is there might be a geopolitical angle to whether certain ideas are accepted or not or criticized. You know, global, not global south. It could be different. There could be regional variations in how people accept an idea or not, you know, in science. So I want to know, have you discovered any geographical or regional variation in people's usage of Kappa, the acceptability of your findings or not? Has there been any such dimension you've investigated?
Yeah, I've interacted with scientists from all over the world. If there are cultural differences, I interact with a lot of Brazilians. Brazilian culture, the people are very comfortable with, at least the Brazilian scientists that I interact with, they're very comfortable in stating their opinion. And they're not too intimidated by higher authority. There's some cultures that are very traditional that where respect for seniors and respect for authority is either highly valued or highly enforced, like some Asian cultures. I mean, I have so many Asian students who, you know, the reason they've come to the United States is they said that they cannot get a good education in science in their countries due to that exact cultural phenomenon. That if questioning seniors is culturally impossible, then you can't do good science in that environment. I've interacted with a lot of Africans who said that in Africa, there's some of that same culture, respect for seniors. But what I've seen from a lot of African scientists is that they've been very rapidly interested in adopting new ideas. I think maybe because they haven't yet been so brainwashed by so much of the scientific literature. They're people who are learning the technology for the first time, they're open to adopt all sorts of ideas. But if ever you feel that you're in a social environment where you're afraid to ask a question or you're intimidated socially, then that's just not an environment where science can thrive. And it's sad that so many people, they've actually had to leave their countries in order to do good science. Yeah, I mean, this whole business of just making up facts and or just making up things and presenting them as fact, I mean, behavior like that can get you to be things like President of the United States, but that's politics. Hopefully science is something different than politics. And but science requires us to feel comfortable in having conversations. And so I think that's what we have to constantly realize, that because scientists are humans too, and we are under social pressures, but we have to do as much as we can to have open conversations, but you have them in respectable ways, but you have to have them sufficiently firm to motivate people to improve.
Thank you. Thank you.
Well said, Prof. Well said. So I think we're really 4:10. So I will close the webinar of today. Thank you, Prof. It was really, really lovely to have you speak with us today. Thank you for volunteering. So I just send out random emails and Prof volunteered, so I really, really appreciate it. I think it was really inspiring. We have lots of people who really, really enjoyed it. And hopefully they will, as you say, also now spread the news.
Yes, that's one thing you can do. Get your hands on the link from this webinar and send it to your friends, especially if